Before the invention of color camera, black and white photos were used to document history. These amazing photos tell us the stories of the past, but the restriction of color limit the storytelling. With the progress in the machine learning field, we are now able to get a better glimpse of the past by colorizing these time capsules and view history in color.
And we are Group 104, and this is our motivation to do the image colorization project. As said before, our main goal is to train our model in order to take a black and white image and try to colorize it. We are using the paper from Zhang, Isola, and Elfros about colorful image colorization as our guideline to do this project. And the same as the paper, they are using the ImageNet dataset, which is more than 1.2 million images. We are also using the dogs with over 20,000. And we are also using the celebrities dataset. Both the dogs and the celebrity were made more specific class, so we can get better prediction in faces and animals. As our methodology, we are using an architecture that has as an input a grayscale layer image, and we want to predict the color AB, the color space AB of this image. And to do so, we are using a 8-block convolutional layer, and each block will have between 2 and 3 layers inside it.
But using a CNN to colorize a grayscale image was nothing new when this original paper was written. The interesting thing was that they came up with using classification instead of regression when doing this. If you look at this image of yellow and blue flowers, and you're using regression, you pick out the colors in the spectrum, and then when you're predicting, you're probably going to end up predicting the mean, which gives you something like this. That's not really what you want. Instead, you're using classification, and then you pick out the yellow and you pick out the blue colors, and you end up with 2 distinct classes, which means that you're not going to end up with something in between. It's going to be either blue or yellow. But if you use classification, you have another problem. You probably have an imbalance in the data, and in this case, if you look at this original image with the true colors, you see that you have a lot of brown and gray and kind of colors that are close to the middle of this gamut. And if you're just doing classification, when you predict, you're probably going to end up with a lot of these colors. So you have an imbalance problem. And if you do that, you'll end up with something like this. So to counteract this, you look at your data set, you look at what colors are more common, and then you reweight them. So in the loss function, you give a higher loss to colors that are much more uncommon because you don't see them as often. And with rebalancing, you get this.
Next, we took the network and we trained on the 3 data sets, and then we went to validate results. The first test we did was a Turing test, which is what they did in the original paper as well. What we did is we showed participants real and colorized images, and we wanted to see if they could tell the difference. For the most part, people could tell when it was artificially colorized, but there were some images that tricked most people, such as the top 2, which tricked 89% and 63% respectively. On average of the benchmark images, about 40% people thought that they were real when they were in fact colorized. Next, we looked at a more quantitative measure to look at performance. So we chose the Frechet inception difference, which is very popularly used with GANs. It's a measure of similarity between the statistical feature vectors of 2 images, and the lower the score, the better the performance is. Overall, we didn't see a strong correlation with the Turing test and this metric, so we think that maybe the FID is not great for colorization. And as you can see on the images to the right, the middle image is a very good colorization and had a higher FID score, where the bottom one is a pretty bad colorization but had a lower score.
We want to further evaluate the performance of the network. We did this by taking original images, grayscale them, and then colorize them with model. We then feed them through a classifier, in this case Inception v3, and let it predict the labels. The result of that can be seen here. Good in this table indicates images that we thought were natural looking. And with these images, both models on ImageNet and dog were able to beat the grayscale. However, when we picked randomly chosen images, it was only the dog was able to outperform. One thing we noted was that for some classes the correct color is very important. So when our network colorized an image of a vehicle, for example yellow, the network predicted taxi, but it might originally have been red and hence an ambulance. This indicates that this type of metrics might not be suited for our network that wants to create a natural looking image and not necessarily the correct one. Moving forward with conclusion. From the complete experiment, it was observed that Zhang et al.'s method can produce strong colorization, but it does not always generalize well. Our smaller models trained on the dogs and the celebrity was able to take new images in this category and colorize them well, while the ImageNet struggled more. However, this is not something we just struggle with. We're looking and benchmarking with original paper's resolutions, or rather results, which can be seen in this figure. It is observed that we share the same weaknesses and failure modes as they do. This includes bias toward colorization in background color and bias towards sepia toned colors. Another learning we got from this, it is quite difficult to quantitatively measure colorization. While FID worked relatively well, we found classification accuracy not give greater insights when evaluating the images. From the Turing test, we learned which gave the most promising results of what is a most natural looking image and not, which is not weird because it's human beings we want to fool, and did that with some images we managed to do. With that, thank you for listening, and this concludes our presentation. Thank you.